In this video we're going to have a recap on proof by contradiction, and we're going to do that by having a look at three examples. These three examples are pretty representative of the types of questions that we can get out. So if you're comfortable with these three questions, you'll be able to answer pretty much any question that you would get on proof by contradiction. Now there are some general things that we need to be aware of. So for every proof by contradiction question, we have to lay out our work a specific way, and that doesn't change from one question to the next. So we always need to make sure that we're stating an assumption. We're then going to go through a little bit of maths to try and contradict our assumption, and then we need two statements at the end. We need to state clearly what the contradiction is that we've managed to achieve, and secondly, our conclusion. So what's how we managed to prove the thing that we set out to prove in the first place. So apart from the general stuff, there are also a couple of little tricks that you need to be aware of for a couple of the questions. So we're going to have a look at proving that root 2 is irrational. Same for any square root of any prime number. There's a trick that we need to be aware of. So we'll talk that one through. And we'll also have a look at the one where we're trying to prove that there's an infinite number of prime numbers. But we're going to start off by having a look at question 1, where we're using proof by contradiction to show that there exists no integers x and y for which 6x plus 9y is equal to 1. So first things first, I need to write down an assumption. My assumption is going to be the opposite of what I'm trying to prove. So rather than saying there are no integer values of x and y for which 6x plus 9y is equal to 1, I'm going to say there are integers x and y for which 6x plus 9y is equal to 1. With these questions, all these proof questions, you have to get used to writing quite a lot down. So I know it's a bit of a struggle for us mathematicians, but you've got to get into the habit of getting this stuff down on paper. Don't shortcut it. There are as many marks for writing your assumptions, stating your contradiction, and stating your conclusion as there are for the maths in the middle. So make sure that you're writing each of those bits down and picking up all the marks for the question. So I've got my assumption. Now I need to do a little bit of maths. So I've got 6x plus 9y is equal to 1. 6x plus 9y is equal to 1. Well, if I divide this by 3, these are both factors of 3, I'm still going to be left with an integer value, a coefficient of x and y. So divide by 3, I'm going to get 2x plus 3y is equal to 1/3. Well, if x and y are integers, that's going to mean that that's going to imply that 2x plus 3y is an integer. Don't know what the integer is, but if x is an integer and I multiply it by 2, I've got another integer. Y is an integer, I multiply it by 3, I've got an integer. If I add two integers together, I've got an integer value. But they've just told me, we've just worked out that 2x plus 3y is equal to 1/3, which is definitely not an integer. So we've achieved our contradiction. So we've got our maths, we've worked through, we've got 2x plus y is an integer, 2x plus 3y is 1/3, which is definitely not an integer. We've got our contradiction. I need to state that clearly. So this contradicts my assumption that x and y are integers. So almost there, we've stated the contradiction. The final piece that I need to do for every proof question, not just proof by contradiction, is to state my conclusion. Therefore, there are no integers x and y such that 6x plus 9y is equal to 1. So this conclusion, this final line, is pretty much rewriting your question. Show that there exists no integers x and y for which 6x plus 9y equals 1. So you're going to get a mark for repeating the question. Therefore, there are no integers x and y such that 6x plus 9y equals 1. If you don't put it on the end, you don't get your mark. Similarly, if you don't state what your contradiction is, you're not going to get your mark for that either. So probably for that question, 4 marks maybe, 1 for stating your assumption clearly, 1 for the little bit of maths, 1 for stating your contradiction, and 1 for stating your conclusion. It's all about writing stuff down for these questions. Right, that's question 1. Let's have a look at question 2. This one definitely involves a trick. Once you've seen it, hopefully you can remember it and you can use it for similar questions. So first things first, we've been told to prove by contradiction that the square root of 2 is irrational. So my assumption is going to be the opposite of root 2 being irrational. So my assumption is going to be that root 2 is a rational number and I'm going to call it x over y. I could have called it a over b. Give it a couple of variable names, doesn't really matter what. X over y, but I need one extra condition. And such that x and y have no common factors. So if they had got a common factor, I'd be able to simplify this down. So I'm assuming that my x and y is in the simplest form. So if I'd got 24 over 36, I could have simplified that down to 2/3. So x and y have got no common factors, so this x and y is in its simplest form. This is really important because this is the bit that we're going to end up contradicting. We're not going to contradict the first part of the assumption. It's going to be the fact that there are no common factors that's going to enable us to contradict the assumption. Okay, so we've got the assumption down on paper. So if root 2 is equal to x over y, then if I square both sides, I'm going to get 2 is equal to x squared over y squared. And then if I multiply through by y squared, I've got 2y squared is equal to x squared. Well, that means if I've got 2 lots of something, then my x squared must be even. So x squared must be even. It's 2 lots of something, doesn't matter whether y squared's odd or even, 2 lots of anything is going to be an even number. So if x squared is even, that means that x must be even as well. Because if it was odd, I'd get odd times odd, which was odd. So the only way that x squared can be even is if x is even as well. So if we call x equal to 2k, so again I don't know what the value is, but I know it's an even number, so I know I can write it as a multiple of 2 times another integer. So x is equal to 2k. We can then substitute that back into this equation here. Let's call it number 1. So we sub that into 1. So my x squared is 2k, so 2k all squared, and that's going to be equal to 2y squared. Well, 2k all squared, 2 squared is 4, k squared is equal to 2y squared. I can cancel down, so I've got 2 and 1. 2 lots of k squared is equal to y squared. Well, that means that y squared must also be even. It's 2 lots of anything, something squared. Doesn't matter what that is. It's an integer value squared, multiplied by 2. It's going to be even. If that's even, that implies that y is even. What that means is that x and y share a common factor of 2. So x and y both even. So I'm going to state my contradiction. This contradicts my assumption that x and y have no common factors. So x and y both even. They both have 2 as a factor. So we've just shown over here they've got a common factor of 2. It contradicts my assumption that there is no common factor for x and y. Therefore, I proved my assumption. Therefore, my final line, root 2 is irrational. So what have we done? We've stated our assumption. It's the opposite of what we're trying to prove. So root 2 is a rational number, which means I can write it as x over y. I need that extra condition, so such that x and y have no common factors, so I can't simplify this down. Therefore, we've got root 2 is x over y. We can square both sides. So 2y squared is equal to x squared. So that means x squared is even, which means x must be even. Must have 2 as a factor. We write x as 2k because we know it's even. Put it into the equation. We get 4k squared is equal to 2y squared. We can divide by 2. Which then proves that y squared must be even. So y is even. Y also has a factor of 2. So x and y both got a common factor, which is 2, so we'll be able to simplify that expression down. Contradicts our assumption, therefore we can state our conclusion that root 2 is irrational. When you've got these questions, it's quite common. We've used, for this one here, we've looked at square root of 2. But sometimes when you get the questions, I'm just going to pause there for a second. Okay, so there are a whole series of questions where we're looking at surds, proving that surds are irrational. So it's always going to be a prime number, so it might be square root of 3, square root of 5, square root of 7 if you're unlucky. But we go through the same steps to prove that that surd is an irrational number. So for root 3, we're going to replace our 2 with 3, so we get root 3, rational number. Same assumption that we're going to try and contradict. X and y have no common factor. That common factor is always going to be the number within the square root. So to prove that the square root of 2 is irrational, we end up proving that 2 is a common factor of my x and y. When we've got square root of 3, we end up proving that 3 is a common factor of x and y. Because we do the same thing, we square, we get 3 is equal to x squared over y squared. We get 3y squared is x squared. So we get this factor that 3 is a factor of x squared. Now this is a little bit more difficult to follow than the even and the odd, which we get with root 2. We have to think about 3 being a factor. If 3 is a factor of x squared, it means that 3 is also a factor of x. That's a little bit more difficult to follow. It does take some head getting around, and I might talk about that after the next video. But you go through the same steps, you end up then proving that y squared has a factor of 3, therefore y's got a factor of 3, and then we've got this common factor of 3, which is our contradiction, because we've stated there are no common factors. We've got a common factor of 3 for both x and y, got our contradiction, and then we can state our conclusion. Okay, I'm going to leave it there. One more example on the next video.